Welcome to solverfy.
Okay, so for this problem, you're given a coil that's around a piece of wood. I guess the wood isn't really relevant other than that's the way the coil is held up. And you're given that the magnetic field changes and you're asked how much charge flows through a point in the circuit during this change. So again, we're going to start with Faraday's law. So EMF is minus N d magnetic flux dt, and that's going to be minus N times the derivative of B times A, and then I'll work on this side as well. EMF is IR for a simple circuit of a particular resistance, and I is dq dt. So I'm going to write that in that way. I is delta Q over delta T times R. And so so looking at this, what actually changes? Why is there a time derivative here? Well, the magnetic field is changing. So we can say that this is minus, and A isn't changing, so I'll stick it on the outside of the derivative. So that's delta B over delta T. So now I'll just drop this down, and then I will do the physicist's favorite trick. Mathematicians hate this trick. Bam. I mean, it works well for simple mathematical functions such as linearly reducing a magnetic field. So now we have delta Q equals, so let's worry about magnitudes and drop the negative sign. We don't care about which direction the current's flowing for this problem. So we get this. And delta B, let's write out our givens. Delta B is equal to 3.2 Tesla, because it goes from 1.6 in one direction to 1.6 in the other. So the total change is double what each one is. And then N is equal to 100. Area is equal to 1.2 times 10 to the minus 3 meters squared. I knew there was going to be something clever about this problem when I saw that they already gave you the area in meters squared. Anyway, so 13.0 omega, ohms, not omega. Great. And then if you plug all this into your calculator, perhaps you'll get what I got, which was 0.0295. Oh, there we go. Coulombs.